Okay, part two. Now, where were we when we left off, right? Is there anything else left today? Let's see, okay. I'm wearing this microphone. I just went to the bathroom, so I realized that's probably on, it wasn't too noisy, but that's probably on tape now, right? So, in any event, okay, let's look at the dissolved oxygen cycle. You know, repeating myself as before, if it's got a box around it, it's a model state variable. If it doesn't have a box around it, it's not a model state variable. As with the carbon cycle, here we've got some open things, or things that aren't boxed, which are basically the atmospheric oxygen. Okay, so fair enough. The major issue with atmospheric oxygen is reaeration, and we may talk about that a little bit. So, you know, it's unlimited, right? It only occurs at the surface, but effectively there's no limit. So once again, we have our friends, the three alkyl groups. When they grow, when they produce, when they photosynthesize, they produce oxygen. Respiration, that's our friend basal metabolism, consumes oxygen. Dissolved oxygen is consumed when dissolved organic carbon mineralizes. Okay, you know, organic carbon goes to CO2, requires oxygen. We haven't talked much about chemical oxygen demand, but we heard yesterday in our lecture about the sediment diagenesis model that the sediments produce sulfide, which is a reduced substance, and methane. And the big one in terms of oxygen demand is the sulfide. Okay, so that goes from hydrogen sulfide to sulfate almost immediately in the presence of oxygen. Sediment oxygen demand consumes oxygen. That's at the benthic sediments. And as we talked about earlier, nitrification consumes oxygen. So what else do we have here? Anything else? Let's see. Okay, let me see. I don't know if that's worth talking about. I think the one point I'll point out about just a novelty, if you will, of ICM, and you'll see this if you look at the code or the input variables. Reaeration, effectively, you know, just writing it out, is proportional to a difference, dissolved oxygen saturation minus the actual dissolved oxygen. Okay, so if you've got a big deficit, reaeration occurs rapidly. If you don't have any deficit, you know, it doesn't occur at all. The key, if you will, the problem is in specifying this reaeration coefficient. And there are many different ways of specifying that. Classically, O'Connor and Dobbins, what's the date on that, 1958, what they said was that in streams, reaeration is proportional basically to the bottom shear stress. And what we're saying is that shear stress at the bottom produces turbulence, and the turbulence turns the water over, and that improves reaeration. Okay, I mean, that's simple enough, and that's a classic equation. Well, how relevant is that to, let's say, the main stem at Chesapeake Bay, where the bottom is 10 meters or 20 meters or more removed from the surface? And the answer might be not particularly. Typically, in big, wide open bodies of water, like the ocean or a big lake, you don't look at turbulence generated by shear, you look at wind. And effectively, it's the same thing. You're getting turbulence, which is turning the water over and improving reaeration. Only the source of the turbulence isn't shear at the bottom, now it's wind. So which of these is most important in Chesapeake Bay? Well, Well, you know, that's easy to, you know, you say, you know, for the main stem that might be, but suppose we go up to upstream in the James River near Richmond. How much wind is up there, or is at the bottom? And actually, I wrote a paper on this one time, and I calculated what we used to do was we computed both of these and took the biggest value. Okay, and I forget the exact results of that paper, but you know, it showed what percentage of the time wind was dominant and what percentage of the time bottom friction was dominant. And we used to calculate both of these and take the biggest value. There's also an option in the model code, just give it the number. Specify a reaeration coefficient and be done with it. And interestingly enough, in this version of the model, this is what we do. Frankly, in the bay, it's not a critical parameter because, you know, the bottom is anoxic, but the surface is not. You know, it's in touch with the atmosphere and it's pretty close to saturation. So it's not, as I said, in the bay, it's not really a critical value. I mean, if you think of bottom water anoxia, what's critical is vertical diffusivity in the water column. How quickly can you get the oxygen from the surface to the bottom? So I'll just mention, you know, since this is a lecture on ICM, I just want to mention to you that you have, you know, in the code, you have the options to do one of three things. Bottom shear stress, wind, I'll give you a number. Maybe in retrospect, I would go back and compute it both ways again, I don't know. But in any event, something else is worth mentioning on this. Very recently, our colleagues at VIMS, we owe them a debt of gratitude. I was using an equation for dissolved oxygen saturation that was developed by a fellow at VIMS more than 30 years ago, and he's long gone, and where did that come from? We're no longer even sure. But our friends at VIMS looked at it and decided that it didn't do a very good job of computing saturation dissolved oxygen at high temperatures. Really high, 30 degrees centigrade, that sort of thing. But we went to the Geological Survey, and you know, these folks are really thorough when it comes to things like this, calculating dissolved oxygen saturation. What they said is that dissolved oxygen saturation is a function of temperature. It's the freshwater saturation, which is a function of temperature. That's modified by salinity, and it's modified by pressure. And the freshwater saturation concentration, look at this function of temperature, my lord, and it's Kelvin. You know, the Geological Survey doesn't fool around. What have you got? A first, second, third, and fourth order polynomial or something there. But in any event, they do a good job on this. Okay, so we use their relationship for saturation concentration in fresh water. And then we also use their relationship for the salinity effect, which looks like that one. And we say that since reaeration occurs at the surface, the pressure effect is just unity. We're not going to worry about it. You know, if you're at the bottom of the ocean, the saturation dissolved oxygen concentration is going to be different because you got an enormous pressure from a mile of water above you, but at the surface of the bay, we're not going to worry about it. So this is new in this version of ICM. As you can see, it's written up in these kinetics, and you know, if you get the code that we're distributing, you'll have this relationship. Yeah, go ahead, Jim.
Question. So the pressure is pressure in the water as opposed to looking at sort of air pressure. The reason I'm asking is we had a project where we had to do some oxygen modeling in Denver near Mile High, and the saturation there is different than we are in coastal water. So is that correction, is that pressure in the atmosphere, or is that pressure actually
I think
in
it's
the water?
pressure as atmospheres. It's pressure in the water.
It is the pressure in the water. Okay.
It is the pressure in the water, yes.
Oh. And would that change as a function then of the altitude? Because I'm trying to figure out if you're really computing saturation at the surface where it's important, why would you worry at depth? But maybe there is a reason for them to do it.
You know, I don't know why, you know, but if you wanted to know what the saturation was at the bottom of the ocean,
You could do it. Oh.
you could do it, yeah.
Actually, it makes a difference if you're aerating at depth.
Oh, that's the
That
aeration
makes a
part.
huge-
Okay.
Huge difference in solubility.
In solubility and transfer.
There you go.
Okay, thank you.
Carl, could you go back for the rearation equations?
The rear,
Rearation equations? I have a question. Yeah, here. Right.
this one,
Yeah, like now the
next one.
O'Connor-Dobbins or stream. So here is that stream velocity and the depths.
Yeah.
So when you apply in ICM, let's say if I choose this equation using stream velocity and the depths to calculate the rearation, for example, our 30 box case, so the ICM tracks the entire depths and calculate the velocity.
Yeah,
Not only the surface layer.
you know, I would need to, I'm confident we use the entire depth. For the velocity, I'm not sure if we use depth average or if we use just the surface velocity.
Because if it's tidal, could cancel out.
Okay, you can't use tidal average velocity. You have to use, that's a trap that,
Magnitude.
Yes.
excuse me,
You have to use a magnitude.
instantaneous velocity. It has to be.
Because otherwise the tidal average might be close to zero.
No.
Right.
I mean, because of tidal, the surface may go out,
Right.
and the bottom may go, goes in. But you have the different directions. So when you do the average layer average
It
velocity,
could be zero.
could
Yeah.
be zero. What I mean is, so are you taking the magnitude?
I think we just use the surface
Just use the
velocity.
surface.
I think. I'd have to
But
check.
depth is the entire depth, not the surface layer depth.
Depth is entire.
Oh, okay. Thanks.
I mean, I think some of the things you're addressing are reasons that it is probably not good to use this equation in,
It's possible, yeah. What I mean is, if just in case, we selected this.
yeah.
Well, yeah, I guess it would be, you want to use that in the river system,
Yeah.
and then maybe go to the wind and measure it, or as Carl does, you just go with it. And actually, that is really what you're going reiteration coefficient, it's a minor difference, is actually a mass transfer. Because reiteration is really just per day, and you're dividing by the depth, so, but anyhow.
Fair enough. Is there anything else worth talking about in dissolved oxygen? We went over the saturation, which is new. We're going to talk on Wednesday morning. Now, this is Wednesday. On Thursday morning, we're going to go over the software we use and the relationships we use to compute heat transfer. Kyle,
Yeah, sorry, I'm just a little confused still on the rearation. So the KR term, you compute the instantaneous velocity of the entire water column?
I think, I'd have to check the code. I'll do it at lunch. I think we use the instantaneous velocity of the surface.
Okay.
But I'm going to check that. I got a date at lunch. I'll check that and get back.
I'm still a little confused in the mechanism. Say if you have, because the rearation occurs at the surface, right? So if you have one velocity, two locations, same surface velocity, but different depths. So if we are using the surface velocity and the water column depths, so we are getting different rearation to the surface layer. Because when we calculate rearation, it's only the surface layer
Right.
and the air that is exchanged. Then the rest of the layers is through the water
Right.
mixing.
Well, if I can just
Go
comment,
ahead.
I think when you look at O'Connor-Dobbins, and the date of that paper was 1952, so mathematical models were, the type of that we're running here, they basically came up with using observations,
Right.
and nobody segmented it. So now,
Right,
and
right.
we face the same problem Carl's
Yeah, that's
done, is
the-
how
the
to take
discrimination.
O'Connor-Dobbins and put it into our finite difference code. And I think we do the same thing that you think is just use the surface layer. So it may not be the best approximation, but I think as Carl was saying, it may not be that important in the bay, and maybe the best way to do it is what you're also recommending, is just go and specify the, you know, the reaeration coefficient, and just live with that.
What the depth is actually, it's the scale for the size of turbulent eddies. So, well, there you have, that's why, now, all right, so don't do this in stratified water because the turbulent eddies are affected by stratification. But what depth is in that equation is the size of turbulent eddies.
That makes sense.
Get that paper, it's a classic. It's seriously, read it, and I'm way off topic, but you know, there's also a reference there to a paper by O'Connor on how to do wind reaeration. O'Connor, 1983. Get the paper, guys. It's a good one. You know, I read old papers like I'm a scholar of Latin or Greek or something. I love to go to these old papers, and it's a really good paper.
If the depth increase, the velocity at the surface will decrease, right?
Excuse me?
When the depth increase, the velocity at the surface will decrease, right?
Well, I don't know.
So it still makes sense, I think.
It depends on whether it's a wind, the mechanism of the velocity. Right?
Okay. As I said, is there anything worth mentioning more here? Okay. Tomorrow morning we're going to go over the software and how we compute heat transfer. But we compute temperature, as we mentioned, from way back. We decided it was easier to compute it than it was to take it from the hydrodynamic model and store it. And this is another classic. I was brought up on Edinger and Geyer. That's right about the time I was a graduate student, and I used to do a lot of work in modeling heat exchange ponds for power plants. That's how I cut my teeth. So this comes from Edinger and Geyer, and basically, in effect, it's analogous to the reaeration equation. What it says is there's an equilibrium temperature, at which point there's no exchange of heat with the atmosphere. The water surface is in equilibrium with the atmosphere. And what it says is the change in temperature is proportional to the deviation from the equilibrium temperature. And you could think of this as something analogous to a mass transfer coefficient. And tomorrow we'll get into the details of, effectively, you need to compute this equilibrium temperature, and you need to compute this K, this rate coefficient, if you will. And we'll talk more about that tomorrow. Salinity, there's really nothing to say. It's in our model, a conservative substance. We compute it for two reasons. One is a couple of reasons. Largely, it impacts dissolved oxygen saturation. And we also use it as a tracer, if you will, to, if you want to be thorough when you do your linkage with the hydrodynamic model, you compute salinity in the hydrodynamic model, you compute it in the water quality model, and they ought to be damn close. If they aren't, you got a problem. So there's some reasons to compute salinity. That said, I'm going to get on to the next lecture. So before I do that, I'll give you a last opportunity, questions or comment. No, it's fine. That's why we're here, right?
Right. So I have a question back to the light calculation on page 6.
Page 6? Oh, that's a way back. Huh?
Yeah, sorry.